So last time we talked about ideal gas mixtures, how to calculate changes in properties of the mixtures. I really didn't emphasize enough about changes in entropy. We talked about changes in internal energy, which is very, very similar to changes in enthalpy. Also talked about specific heats of mixtures. We really need to solve problems because that's where rubber meets the road. We need to be able to solve a problem where you have a closed system, an ideal gas mixture, as well as an open system where the fluid is an ideal gas mixture. So in review, when you have a question like I need to calculate the change in, let's say, the internal energy or the change in the enthalpy of an ideal gas mixture, you could, either one, they're very similar, so let's just talk about the enthalpy change. You could do it on a molar basis or a mass basis. Okay, so a molar basis, we say, how many moles of species I do I have in this mixture? And you're going to sum over all the I's, all the species. And then you'll have a change in the enthalpy from initial state 1 to final state 2 for that species. And it's on a molar basis, that over bar. So we'd sum over all of the components. All right, likewise, on a mass basis, you'd sum over all of the components. Instead of having the number of moles, you would have M for the mass, and then you would have the H2 minus H1 without the overbar because it's now a specific enthalpy per unit mass for each of those components. All right. Now, when you get to entropy, it's a little more challenging. So let's go talk about entropy. So we say, how do I normally calculate the change in entropy for an ideal gas? Probably you remember an equation like this. Let's say the mass times S2 naught minus S1 naught minus R natural log of P2 over P1. Something like that. Okay, as a review, what is this R right there? Gas constant, which is R bar divided by the molar mass of that gas. What are these two P's here? This P2 and P1. Those are pressures. Initial pressure, final pressure. All right. And then you have this S2 and S1, but the superscript naught. What's that superscript? Looks sometimes like a letter O, and then sometimes it looks like a number 0, but it's really like a letter O. Okay, so what's that superscript naught indicate? Atmospheric pressure, low pressure. So basically this has the effect of the change in temperature, and this term has the effect of the change in pressure. So, do this. What is this term if P2 is equal to P1? Natural log of 1 over 1? 0. Right. And then what is this term if T2 equal to T1? 0, because these are only a function of T. These are only, you would sometimes put T2 and sometimes put T1, but that S naught is only a function of temperature. You can look it up as a function of temperature in the tables. Let's assume constant specific heats. Well, then you'd write C sub P, natural log of final temperature over initial temperature, minus R natural log of P2 over P1. So what's the difference again between this equation, variable specific heats? You need the tables to get the S naughts. And then this one, and actually that S naught's only for air. Well, no, it's not just only for air. It's for air and then also for the ideal gases that you have tables for. We only have a limited number of those. See, what is that table 23? Table A23. And in table A23, I can't write. Table A23. You have it for carbon dioxide as an ideal gas, carbon monoxide. You have it for water vapor that behaves as an ideal gas, oxygen, and nitrogen. Okay. But you can get specific heats for many more ideal gases than these that are listed where we have tables. Okay, so if you have an ideal gas that's not in this list, then you're forced to use constant specific heats. So this is constant specific heat. All right, what happens if I have a bunch of these in my mixture? Well, do a little sum, true, over each component, and there you go. Now, it raises a few questions like C sub pi, does that make sense? Should I talk about the specific heat of the nitrogen in the mixture and the oxygen in the mixture? Yeah, that makes sense. So that specific heat of that it depends on the component. Do I talk about T2I and T1I? Do I have a partial temperature concept? No, there's no partial. If it's in a gas mixture, there's one temperature that represents that temperature for that gas mixture, not partial temperatures. But when I come over here, I have P2I there and P1I. Are those the partial pressures at the initial state of component I? Yes, they are. We do have partial pressure concepts. And then is this R, which is R bar divided by the molar mass of I? So maybe we put an R sub I. Yeah, that R depends on what component you have. The way it's written on a mass basis. You can also put it on a molar basis. Put the number of moles, I, Cp bar, natural log T2 over T1, minus R bar, natural log P2 over P1. And sometimes we just leave everything like out here, I, or if you want to emphasize, it's like P2I and P1I, but not R bar I. There's R bar is the universal gas constant. It's not T2I and T1I, no, but it is Cp bar I. Okay, and then you sum over all of the I's. So a little tricky, but you have to deal with the partial pressures when you calculate changes in entropy of ideal gas mixtures. All right, let's press forward. So here's a problem. It'll take us a while to solve this problem. I'll try and go as fast as I can so you don't fall asleep. Initially, you have 0.36 kilomoles of nitrogen at 500 Kelvin, 300 kilopascal in a rigid, well-insulated tank or container, connected to a second rigid, well-insulated tank containing a different amount of a different gas, hydrogen, not nitrogen, at a different initial temperature and a different initial pressure. A valve between the two tanks, assumed, is opened and the gases are allowed to mix. After they mix and you wait a long sufficient time, guess what? You'll get an equilibrium state where there's one temperature that characterizes the temperature of the gases regardless what side they're on, they're mixed. So they come one temperature. So you think, maybe you draw an illustration to help. Here's a tank. Here's a valve that you control. Here's another tank. Okay. Initially, pure nitrogen on one side. Let's call this side A. We're starved for subscripts. We need to, what type of subscript to help identify things. So sometimes I'll use subscript 1 for state 1, subscript 2 for final state 2, and then maybe this tank A and tank B. Or instead of tank 1 and tank 2, then you get all confused. What are the subscript meanings? But anyway, tank A and tank B, after they mix, the nitrogen's not pure anymore. And the hydrogen's not pure anymore. They're well mixed, and they have one equilibrium temperature. So the question is can you find and calculate the final equilibrium temperature? So how would you go about doing that? The two initial temperatures? Right, you know that final temperature, let's call it T2 without a subscript other than just 2. And maybe we talk about the initial temperature T1 in tank A. You could use that type of subscript. Or you talk about T1 of the nitrogen, the initial temperature of the nitrogen, which is isolated only to tank A. Either way, you have to have some subscripts to know what you're talking about. And we know that temperature is 500 Kelvin. Likewise, we could struggle with, okay, what about the temperature initially for the hydrogen, which is temperature 1 in tank B, which is 300 Kelvin. This temperature and that temperature. Okay. You allow them to mix. They come to an equilibrium temperature. How am I going to calculate that value, that equilibrium temperature?
Just calculate the mole percentages.
You can do that, and you'll need that actually for the second part to this problem. There's part B, but I don't want to overwhelm you. Let's just solve part A first. Somebody says, I'm in San Antonio, I have a problem, I want to drive to Houston. What do you tell them? You tell them, get on this interstate called I-10 and start driving east. I mean, I'm kind of asking you for that high level type of, how do I approach this problem? I'm trying to find T2. What am I going to do? Introduce, you're either going to have an open system or closed system analysis. And so for this problem, do you think we're going to have a control volume where mass can flow across the boundary of it? Or do you think it'll be more of a closed system analysis? Closed system. Now we have to pay particular attention. What is our closed system? Would it be only what's, the contents inside of A? No, it's going to also come across and include what's in B, won't it? Now we're going to neglect the volume of the little pipe and the valve connecting them. The volumes of the system are just volume of A and volume of B, and those tank volumes. Okay, so what type of equation do I want to write for this closed system? We're going to do an analysis of this closed system. What type of analysis would I like to? I'm in the thermodynamics class. It's all about energy. Start with the 18th law of thermodynamics. No, start with the first law of thermodynamics. All right, I feel like a dentist pulling teeth. Can you write the first law of thermodynamics for a closed system? Starting in initial state 1 and ending at final state 2 for any generic system. Don't strike terms too early. Can you do that? I'm going to pause, walk around. So we would say how the change in the internal energy and the change in the kinetic energy and the change in the potential energy, okay if you struck those right away because it's pretty obvious if you solved a few problems, it's like, no, those terms are zero, is equal to the rate, not the rate, it's the amount of heat transfer in during the process from initial state 1 to final state 2 minus the work done 1, 2, either shaft work or boundary work. So now we take a look, we already struck these two terms. What about the heat transfer? Well-insulated tank, zero. What about this work 1 to 2? Zero. Why again? There's no shaft and there's no expansion pushing back boundary or anything, pushing back the face of a piston. So what do we have? We have that U2 minus U1 is equal to 0. Is that a lowercase u or uppercase U? Uppercase U. So how do we calculate the change in internal energy for an ideal gas? I know initially it's just the component by itself, nitrogen by itself, but then it also gets mixed at the final state. So anyway, you would do this, you would say this is equal to the U2 minus U1 for the nitrogen plus U2 minus U1 for the hydrogen. That makes sense? The sum of the changes have to be 0. I have two components. So I don't write it as an infinite sum, just the sum of two changes. Okay. So it's 0 is equal. Do you want to work on a mass basis or a molar basis? Either way will work. They tell us, though, to use down here, what do they tell us to use? These V's, C sub P's and C sub V's. Did they give me the C sub P and C sub V on a molar basis or on a mass basis? It's a mass basis. No bars on those. So you're going to have to go one way or the other. It doesn't matter. You just have to do it correctly. Either do it all in kind of a molar basis or all in the mass basis. True? So let's, which way do you think would be a little better or want to see me work it out? Mass basis? Okay. Guess what? You'll have to convert this amount in moles, kilomoles of nitrogen to M of the nitrogen. How would I calculate the mass of the nitrogen given the N of the nitrogen is 0.36 kilomole? Multiply by the molar mass of the nitrogen. You go look that up in the table. It's around 28. Okay, so we're going to get that the mass of the nitrogen times, now I want to change in the specific internal energy of the nitrogen, and I'm going to use these constant specific heats. Which one is it? But the volume of the nitrogen isn't constant. It just expanded into the other tank. This thermodynamics is all trash. No, this is just one of those conundrums. It's hard to understand. Why would, yeah, but that's the right term. CV, the nitrogen, did it undergo a constant volume process? No, it's spread out. But that's the right way. This is CV times T2 minus T1 of the nitrogen. This is CV of the nitrogen. I'm adding a lot of subscripts so that you know what to put in. Plus the mass of the hydrogen, CV of the hydrogen, times T2 minus T1 of the hydrogen. I like to do this. Do I know the initial temperature of the hydrogen? Yeah. The CV of the hydrogen on a mass basis, I come right up here. Yep. The mass of the hydrogen, I'm going to calculate it by the number of moles times the molar mass of the hydrogen. Doable. I can get that. Initial temperature of the nitrogen, CV of the nitrogen, mass of the nitrogen. What's the only unknown? Final temperature. At this point, I'll just say that T2 is equal to mCV of the nitrogen times T1 of the nitrogen plus the mass, specific heat, constant volume of the hydrogen times the initial temperature of the hydrogen divided by mCV of the nitrogen plus mCV of the hydrogen. You solve a few of these like mixing problems, you know, take something hot, something cold, put it together. You see the pattern. This is the general pattern for the final equilibrium temperature. It works for ideal gases. It works for a lot of other things. So we stick in our numbers. There's the answer, 444.6 degrees Kelvin. You do a little check. Is it between the high temperature 500 and the low temperature 300? You know, I would look for an error if my final temperature was either above 500 or below 300. It doesn't make sense. There's no, yes, we're going to do combustion where we have reacting mixtures where there's exothermic, liberation of heat due to chemical changes, the bonds change, but that's not this chapter. All right. Guess what part B is going to ask you to do? Something with the second law of thermodynamics. So now they say calculate the entropy generation during the mixture or the mixing. So we still have our same two tanks, little valve in between. We open them up, and do you think this is going to be a reversible process or irreversible mixing process? Highly irreversible. Think about the challenge to say, I've got this mixture of nitrogen and hydrogen, and I want you to somehow make all of the hydrogen go over here, all of the nitrogen go over here, and make the nitrogen hot and the hydrogen cold. And oh, by the way, the pressure of the nitrogen needs to be really high compared to the pressure of the hydrogen. This is a very irreversible problem. So, entropy generation during the mixing. What symbol? Like for part A, I said, oh, I think I'm going to look for T subscript 2. What symbol should I pick for the answer for part B? What am I looking to calculate? Sigma or sigma dot? Is there a difference? There is a difference. It's sigma. And if I like to sometimes add a subscript 1 to 2, not state 12, but saying during the process from 1 to 2, there's amount of entropy that's generated. Okay. Clicker question. I like to do this. I like to think of what are the typical SI units on T, right? Somebody says Kelvin. No clicker question there, right? But what are the typical SI units on sigma, either with or without the subscript 1 to 2? So it's the amount of entropy generated during the mixing process. Would it be answer A, kilowatts per Kelvin, answer B, kilojoules per Kelvin, or answer C, kilojoules per Kelvin kilogram? And we're off and running. You have a question? Well, let's do this. Let's write the second law of thermodynamics. Who can lead me through the most general form, second law of thermodynamics for a closed system undergoing a process, initial state 1 to final state 2? What does the second law look like? S2 minus S1, or delta S, the change in the entropy. It could go up if there was some Q 1 to 2 bringing in entropy as it crossed the boundary. The temperature of the boundary is key in the bringing the entropy in, TB. And then I have one other term, sigma 1 to 2. True or false? Does this equation look good? There's a principle in science and engineering that if I take A equal B plus C in general, that the units of A and B and C, if I just have equations, like, have to be the same. So if A is in meters, B is meters, C is in meters. You can't have A in meters, B in meters, and C in meters cubed. It don't make any engineering sense or physics sense or anything else. True? So if I'm looking to figure out the SI units on sigma, I can think about maybe I could figure out the SI units on delta S or one of these. I repose my question. What are the SI units of sigma? Answer A, B, or C? What do you mean capital A? You just punch your letter A. All right, so this is where I pick it up and I get to ask one more question. So let's do this. How many people have a really firm idea the units on Q, the typical SI units on Q, the amount of heat transferred during the process from initial state 1 to initial state 2? Could you volunteer? What do you think the units on Q are? Kilojoules. I think he's right. All right. Now, somebody else, really tough one. Temperature. What are the typical Can I divide by, what are the units of temperature for TB that I need to divide by? You want to help the whole class? He's going to help you. All right. Now we're going to go back and we're going to ask the same exact question. What are the units for this sigma that we're looking for? Answer A, kilowatts per Kelvin. Answer B, kilojoules per Kelvin. Or answer C, kilojoules per kilogram Kelvin. You are a great help. You are a great help. I can tell the students in this class they have benefited from your input. You ready to grade it? Yeah, you've been ready to grade for a while. But now you see you're ready to grade. But were you ready just a little while ago? Huh? Remember, look at your options. They didn't change. True? And the first one, which means basically the first time you were, as a class, I would suspect a lot of people were guessing. I'm just suspicious. Anyway, let's press forward. It's really nice to know what you're asked to calculate and what are the anticipated units, and then what is the sort of range of this. Do you think that sigma, if I calculate it, could be less than 0? Do you think I could get a negative sigma? Yes, it's possible. Answer A. No, it's not possible. Answer B. If I get a negative sigma, is it okay? Yes, sometimes I can get a negative sigma. Answer A. Or no, I never can get a negative sigma. Answer B. There was a whole chapter. It was talked about how you can't destroy entropy. It was called the second law of thermodynamics. It limits the transfer of energy between forms. It's kind of a pain for us as engineers. We'd like to burn something, turn all that thermal energy into work. But it can't be done. It cannot be done. All right, so there are things that are limitations on the transfer of energy. There you go. Well, now let's get on to the task of solving this problem. So how am I going to solve for that entropy that is generated during the process? Well, I'm going to start with the second law of thermodynamics, true. And for this problem, one of these three groups of terms, either this group, let's call it, no, forget it, no more clickers. Come on now. This is 0. No heat transfer to the surroundings. So if I want to calculate sigma 1 to 2, I need to calculate S2 minus S1. Well, I have two components. I'll do the same thing. I'll calculate the change in the entropy, delta S, for the nitrogen, and I'll add it with the change in the entropy for the hydrogen. Does that make sense? And so this will be the mass of the nitrogen times. I have constant specific heats, so that's nice. And I really have a couple equations. I'm looking for a change in the specific entropy of an ideal gas. There's two equations that you might be tempted to use, but they're both equivalent. You might be C sub P, natural log of T2 over T1 minus R, natural log of P2 over P1, or C sub V, natural log T2 over T1 plus, not minus, R, natural log V2 over V1. This is the one almost always used, but every now and then this is very convenient. Both are available to you. You've known them, used them. So we put in here, we put in the C sub V. I'm going to emphasize it's the nitrogen C sub V. The natural log, T2 divided by T1 of the nitrogen. Why don't I put T2 of the nitrogen? Because I already talked about that. It's just the final temperature. So don't make it more complicated, but let's put in the R bar divided by the molar mass of the nitrogen. And we have the natural log. Now we have the final pressure of the nitrogen, and we have the initial pressure of the nitrogen. And I'm going to add to it the mass of the hydrogen times C sub V of the hydrogen. Oh, C sub P. Sorry, did I write C sub V? It's C sub P. C sub P of the hydrogen, natural log T2 over T1 of the hydrogen, minus R bar divided by molar mass of the hydrogen, natural log P2 of the hydrogen divided by P1 of the hydrogen. All right. I think I got it all down. Did I make any other errors? Thank you for being very alert, those that caught that. All right. Now, we have the CPs, We have the R bar, no molar masses. We just calculated the final temperature. We know the initial temperatures. We know the masses. We had to use that from the previous problem. Okay, the hard parts, the pressures. What is P1 of the nitrogen? Okay, the nitrogen always starts in container A. It's pure nitrogen. Is there any nitrogen over in container B to begin with? None. None. So the partial pressure is equal to the total pressure initially in the side A of the tank. So this pressure right here, P1 of the nitrogen is 300 kPa. All right, with that, what is P1 of the hydrogen? 70. All right, we've got two of those that are hard. That was pretty hard to work out, but now we have some really hard ones to work out. All right, it's going to be multi-stepped. You just can't look at it and say, oh, this is the answer for what is the P2 of the nitrogen? What is that partial pressure of the nitrogen at the final state? I'm going to have to get the final pressure at the final state because I got some tank that's 300 kilopascal and some tank initially started at 70 kilopascal. I suspect the equilibrium pressure will be in between somewhere. But it's not obvious what it is. I'm going to have to work to get it. But once I get P2, then I'm going to multiply by Y of the nitrogen. What's that mole fraction of the nitrogen at the end of the mixing? All right. Likewise, this one is going to be the same P2, but the mole fraction of the hydrogen at the end of the mixing. Okay, let's do this. We know the kilomoles of nitrogen, and we know the kilomoles of the hydrogen. What is the equation for Y of the nitrogen? The mole fraction of the nitrogen at the end of the mixing. 0.36 divided by 0.36 plus 0.14. Do you like that? Yes or no? Yeah, that'll work. And so guess what? This is, I'm going to just say we can calculate it with a little work, and we can calculate it with a little work. Now the really hard one. What is that final equilibrium pressure P2? This will take a few steps to get it. Can I give you a few seconds to think about it or just tell you? What do you want? What do you want? Professor? Yeah, I'm sitting here. You're doing a good job of solving this problem so far. Why stop the momentum, right? But I rob you of your education. Yeah, I do. All right, what you have to do is you think, maybe I can use the ideal gas equation to get that final pressure P2, because if I know the final volume of the total gas mixture, and I know the total number, maybe I put volume total instead of V2, volume total number of ideal gas moles, kilomoles, and I have R bar, hey, that's universal gas constant, and I have T2 final. Well, do you think that equation will work? So we have to think exactly, what exactly is each of the terms? T2 is easy, it's the final equilibrium temperature. R bar is the universal gas constant. An individual ideal gas behaves as an ideal gas. I have two individual ideal gases, I mix them, they still behave as an ideal gas. And this is the total number. Guess what that number is? Yeah, 0.36 plus 0.14. What is that? 0.5 kilomole. Okay, so this equation, if I could just get volume total, then guess what? I got P2. All right, so how do I get volume total? Calculate the volume of tank A and calculate the volume of tank B and add them. All right, how do I get the volume of tank A? use the ideal gas equation only for the initial state for what's inside A or tank A. Right. So we have that the pressure initial of the nitrogen times the volume in tank A equal to the number of moles of the nitrogen initially, which is just the same, no reaction occurring, times R bar times temperature 1 of the nitrogen. What does that allow us to calculate? The volume of tank A. Very similar equation for the volume in tank B. You then add those to get the volume total. Should I be more explicit or not? Do you follow it? You got it? And so it's a lot of work to get P2, but once you get P2, let's see if I have a value for P2. I can't see it. Oh, here it is. P2 turns out to be 185.26 kilopascal. Is it between the 70 low to begin with and the 300 high to begin with? Sure. So there you go. Once you do that, then you just calculate the sigma 1 to 2, and it comes in at 0.669 kilojoules per Kelvin. Yes, sir. Any other comments? Do I have enough time to solve another problem? Well, maybe. Maybe if I only talk to myself. How about I do that? Nitrogen. So we have a nitrogen. It's 40 degrees C. So we have a temperature 40 degrees C. It's 200 kilopascal. And volumetric flow rate of the nitrogen is 60 meters cubed per minute. So this is our nitrogen stream. It enters a well-insulated mixing chamber. Here's my mixing chamber. It's just, that's it. Okay, it's well-insulated. And then argon is coming in the other stream. It has a temperature of 110 degrees, so it's hot. It has a pressure of 200 kilopascal. Compare the pressures, they're the same pressure. And the volumetric flow rate is 20 meter cubed per minute for the argon. And the mixture exits at 200 kilopascal. Life is pretty easy when they don't mess around too much with the pressures. But it can be a little more challenging. How would you mess around with, just put a little valve restriction in there. And then now, oh boy, I've got to, I'll have more entropy generation and I'll have to deal with that, okay? Some restriction in there, but they didn't. So part A says calculate that exit mixture temperature. Here I struggle with, do I use subscript A and B and C, or I just say, here is inlet state 1, inlet state 2, outlet state 3. I think that's the preferred choice for subscripts. So we're going to talk about the temperature at state 3, which is the outlet mixture temperature. That's what we're asked to solve. What units do you think will calculate the exit temperature in? Kelvin or degree C? Okay, what's the strategy? Just like baseball, you hit it, go to first. Go to first, don't go to second law, go to first law. Go to base, first base. All right, so we introduce, for this one, it makes sense to have a control volume where I have mass flow rate coming across, mass flow rate coming across, mass flow rate coming across. True? Okay, given the volumetric flow rate, I could probably get the specific volume of the nitrogen coming in at 1. I could probably calculate the mass flow rate of the nitrogen coming in at 1. True? Little work, but I can do it. All right, how about this one? I can do the same thing. Specific volume of the argon coming in at 2. The mass flow rate of the argon coming in at 2. All right. The mass flow rate going out at 3 is the combination of the mass flow rate of the nitrogen and the mass flow rate of the argon. And I bet you I can get the mole fraction of the nitrogen in the mixture going out and the mole fraction of the argon in the mixture going out. See? All right, so now let's go ahead and do the first law. There's a number of ways to do it, but you basically have the mass flow rate of the nitrogen coming in with its enthalpy or internal energy. It's enthalpy of the nitrogen coming in, plus the mass flow rate of the argon times the enthalpy of the argon coming in. Maybe I'll call this state 1, maybe this state 2, equal to, well, we have the nitrogen out and the argon out, and we're going to have the enthalpy of the mixture, but it's almost easier just to say nitrogen out with the enthalpy of the nitrogen at state 3 plus the mass flow rate of the argon times the enthalpy of the argon at state 3. And because we have constant specific heats, we can just do a little algebra. There's no Q dot, there's no W dot, there's no changes in kinetic potential energy, and I'm trying to go fast. That's the first law of thermodynamics. All right, so now we're left with the mass flow rate of the nitrogen times the specific heat constant pressure of the nitrogen times the exit temperature 3 minus the inlet temperature 1 of the nitrogen plus the mass flow rate of the argon, C sub P of the argon, temperature exit minus temperature inlet of the argon equal to 0. Does the algebra look okay? And guess what you get? You get a very similar equation to what we had before. It's just m dot C sub P for the nitrogen times T1 of the nitrogen plus m dot C sub P of the argon times T1 of the argon divided by m dot C sub P of the nitrogen plus m dot C sub P of the argon. Look okay? All right, let's continue. What do we get for an answer? 324.4 Kelvin. Part B, what do you suspect? Calculate the rate of entropy production. What symbol am I going to be looking for, and what are the SI units? It is now sigma dot, and yes, it's in kilowatts per Kelvin. For the same control volume, like that. All right, so we write the second law, and so we have a steady state flow, and so the rate of entropy production is going to be let's do it this way, the m dot of the nitrogen times the S2 minus, or S, let's do this one, S3 minus S1 of the nitrogen. It's the increase in the entropy of the nitrogen stream. And then we have the mass flow rate of the argon times S3 minus S2. This is 132 of the argon. Maybe it takes you a few steps to get to there, but is that a good second law? All right, now this goes back to your question. Hey, can I use this change in entropy? Sure, that's what we're doing right here. It's a change in entropy equation, the mass flow rate of the nitrogen. So we'll use C sub P, natural log, T3 divided by T1, minus R, natural log, of P3 divided by P1. Again, this is the P3 of the nitrogen and P1 of the nitrogen. That's N2. And then let's add to it the mass flow rate of the argon. C sub P of the argon, natural log of T3 divided by T2 minus R, natural log of P3 of the argon divided by P2 of the argon. Let's do some checks. C sub P of the nitrogen, no problem. C sub P of the argon, no problem. T3, we calculated. T1, we know. Those are known. This R is R bar divided by the molar mass for the argon and the nitrogen. So we got it. What is this pressure? P1, the inlet pressure of the nitrogen. Because it's pure nitrogen in that stream, it's 200 kilopascal. And this one, it's 200 kilopascal. This one, you got to get the mole fraction times 200. You've got to get the Y of the nitrogen out times 200. How do I get Y of the nitrogen going out? You can do it by the molar flow rate of the nitrogen divided by the molar flow rate of the nitrogen plus the molar flow rate of the argon. Right? And then you'll do the same thing here for the molar flow rate. So the final answer, when you run it, is going to be 0.430 kilowatts per Kelvin. When you do second law analysis, keep your digits in your calculator. Do not truncate to 3 or 4. Keep them all in your calculator because it's sensitive to round off error. Second law calculations are sensitive, more sensitive than first law to round off error. With that, I stop. Thank you very much for your attention.